Hello and good evening. Welcome to our May 2024 live stream. And yeah, it has been a time since we saw each other. Hope you all well. Um, we've been kind of busy with various projects recently. Um, but yeah, this is another month where you're going to get a new plugin for Lightwave, and you did vote for the cache node, and we did get the initial version working today. So we're going to show you how it works, maybe explain a little how nodal networks are evaluated in Lightwave. And yeah, let's see if you have any questions as well. So let's start. Um, we're obviously going to start with our trusty old Lightwave cow. And since this is a cache node video, it's going to be a cache cow today. Let me just go to the surface for the hide. One thing I've done here is I basically have two image textures that use the same projection, and they will be mixed together using a turbulence texture as basically a blend function between, or using the procedural as an alpha channel to determine which of these two textures is going to be blended in, and that goes into a standard material and that goes into a surface. Super, super simple. If you look at it in VBR, it's going to look like this. Now, the reason why I did it like this is because one thing that the cache node does is if an output of a node, like the projection output here, is used multiple times as an input somewhere, Lightwave is going to evaluate everything to the left of the input multiple times. So in this case, let's say we have a pixel where the turbulence returns some kind of grayscale. So the mixer node up here is going to have to mix the background and the foreground color together and needs to evaluate both of them. So what it does is it gets the background color, which means it needs to evaluate the image sampler. That in turn needs the projection, so the image sampler evaluates the projection node. Um, Next, the mixer is going to need the foreground color, which in turn means it evaluates whatever is connected to it, which is the other image sampler. And that in turn also needs a projection to evaluate properly, which again goes back to the same projection node here in this case. Now, the interesting thing is that the projection node is being evaluated twice, even though the value that is being used by both of these samplers is actually the same. And while in this case, it doesn't make much of a difference in terms of render times, the more complex the things are that are on the left of whatever is being reused, um, the more compute time is being used to compute the same thing multiple times, even though it's not required. So in this case, um, I'm rendering the image with a fairly high amount of anti-aliasing, just to make sure that I have a decent render time to show a difference. And what I will do is I will actually turn down the contrast of the turbulence to like 50%, which gives me more grayscales, which in turn means there's more areas where both image samplers are being used. Because if the turbulence returns black or white as an opacity, then the mixer node is smart enough to either only evaluate the background color, not the foreground, or just the foreground, not the background. But in this case, I'm going to make sure that I'm going to have plenty of grayscales by decreasing the contrast, as you can see here. Now, this is the vanilla setup. I think 128 samples. And yeah, this is a fairly fast CPU. It's a Ryzen 7 with 16 cores. Ryzen 9, sorry. And it should take around 15 to 20 seconds, which is a bit longer because in this case the cow is taking up more of the screen space. But the longer it takes to render, the more of a difference we should be able to measure in the end on how the cache node optimizes things. Oh, come on, come on. To be fair, the reflecting floor doesn't really help. But it also increases render time, which makes the difference more pronounced. Well, we're almost done. Okay, so this took 1 minute and 43 seconds to render. This is going to be our baseline. So, the cache node. We just delete this. Yeah, as I've discussed, basically the projection node here is being evaluated every time the mixer computes one of these color inputs, and which means that it's multiple times per evaluation of the surface. So if I just add the cache node, like so, it starts a bit like the elbow node that you have already. And what you do is you take the output you want to cache, you attach it, and as you can see, it creates a pair of outputs and inputs. And those can be different data types. Not everything, like materials, won't work, but you can have like colors, vectors, scalar values, projections, and even matrices that are being cached. So we now have the output, and what we basically do is we connect this output to the projection here and here. And what the node is going to do now is that for every evaluation on every thread on the CPU, as well as every recursion level, it will cache the last value. So if nothing has been cached, then the projection node here is going to be evaluated, and whatever is the output is going to be cached in the cache node, again per thread, per recursion level. And if the cache node on the same thread and the same recursion level is being evaluated again, then it's going to return the previously stored value. So let's see if this actually makes a difference when it comes to the render time. Again, this should take 1.5 minutes or so. Hopefully a little bit faster, but we'll see. And to be fair, this is a really simple case because the projection node itself is relatively simple. At least in this case, we're using UV mapping, which is a bit more expensive to compute than, say, planar or spherical or any of the other mapping types. Because UV mapping actually has to look at the geometry and the vertex maps that are stored in the geometry. So let's see. 50%, 47 seconds to go, 45 seconds to go. It may not be that much faster, we'll see. And a big hello to Michael Stetson from Texas. Hi, Mike. Long time no see. So 103 seconds is the time to beat, and we should, but it might get close. Okay, 97.3 seconds, which is 1 minute and 37 seconds, which basically means we do have a slight win of about 3 seconds. 3 seconds in total, which isn't that much. But again, this is also a very simple example. And one thing that shouldn't be forgotten is that the cache node actually adds some overhead as well. So even in a simple case like this, you get 3 seconds, but the more complex things are, the more you compute on the left-hand side of the cache node, and the more it's being reused, the more time you're going to save. And yeah, as I mentioned earlier, you will be able to cache different types of values. So the more I add here, the more outputs you have, and everything in here is going to be cached. Oddly enough, there actually is a bounce output here, which is the number of the current bounce. And the funny thing is that isn't actually directly available in the SDK. But yeah, and also one thing the node allows you to do is there's a pass-through. So if you want to disable the cache node completely, you can do that without deleting it or rerouting all the connections. You can just disable it here, and then it's not going to do anything. And I could now re-render the whole thing with the pass-through, and I should be back to the original render time, which was 103 seconds or so. And again, the more often whatever you use here is going to be reused, the more time you save. And you've got some more options like removing different inputs, outputs, removing unused connections. I'm not sure if this is going to work. Let's see. Ah, yes, there you go. So like with the elbow node, because it's based on the same code, you can just remove all the unused inputs, outputs if they're not connected to anything, just to clean up your node graph. So yeah, that's pretty much the cache node. Sorry that I don't have a better sample yet. One thing to note, because we used to have a cache node before, one thing that changed in the rendering process in Lightwave is that the material nodes nowadays, with the big render change in 2018, the material nodes actually do not ray trace anymore. So previously, um, it did make sense that if you used a material multiple times, that you would cache the output of the material, because the material node itself would shoot rays into the scene. Um, the thing is that nowadays the ray tracing of the materials doesn't actually happen in the material node, but it happens later in the shading model here, which is like the integrator. So basically, um, the material nodes, they compute weights of the different shading components, how much reflection, how much transparency, how much color, luminosity, yada, yada, yada. And those values get combined if there's multiple material nodes, and then get passed to the photoreal shading model, which then starts shooting rays into the scene and says, okay, um, I've got this percentage of reflection and it's this and this blurry, so I need to shoot that many rays into the scene. All of that happens here. There is no cache file. Kevin Washington asks if there's an option to control where the cache file is located. There is no cache file. What is being cached is the evaluation of the node graph um, the evaluation of the node graph as it's being rendered or whatever. So the point is that if you have a node output, like the projection here, that's being used multiple times, like here or here, then if Lightwave computes this, then when the image sampler 1 is being computed and the color output is being used, it needs to compute the projection. If image sampler 2 is being used, it again computes the projection node um, on the same thread and the same recursion level, that is. Um, and the point of the cache node is basically to say, oh, wait, I've already computed the output of that node. I don't need to recompute the whole node again. I can just use the computed value from the last evaluation. But that is the evaluation on, in the case of a surface shading, the evaluation on the same surface of the mesh at the same recursion level. So let me just go back to this. So basically, if let's say a ray, I don't know, hits the cow here, then the cached values for that area or for that point are going to be different than if a ray hits the cow here, because there are different threads, different spots on the surface, um, and it uses things like are we on the same thread, are we on the same recursion level, but also are we computing the same spot on the surface, the same coordinates? And only if those are identical would it reuse the cached values. Otherwise, it's going to store a new cached value. So I hope that that makes it clearer. It should be perfectly fine with coverages. And you mean with using occlusion and reusing that? That's a good question. I would need to build a setup for that or a node graph. To be fair, if you do have a node graph that you think would profit from this, feel free to send it to me. Otherwise, I think I'll be able to send this out by Monday or so. So you'll be able to play with it and give us your feedback. And yeah, sorry for the late stream this month. Um, but yeah, sometimes things happen. Also, as a side note, since we will be pausing our Patreon again, we will be pausing it after the stream just to make sure that you're not being charged next month. And it's the last day of the month. So if you still want to join the Patreon, you can, but not for much longer because, as I said, we won't be charging the next month, so we'll pause again. Oh yeah, sure, sure. Yeah, if you remap a value and it's basically something that I try to do with the turbulence here, where I'm um, kind of using it to mix two different textures. And if you use occlusion to mix even more textures than that, it would certainly make sense to cache that as well, because computing occlusion can be very expensive. Um, in this case, the opacity input is only being computed once, so it wouldn't make sense. But if I had an occlusion here, and I would use the output of the occlusion multiple times in different blending contexts or something like that, then yes, inserting the cache node there would make a ton of sense. Absolutely, yeah. But yeah, not sure what else I can talk about at the moment. If you guys have any questions, feel free to ask them in chat. Yeah, if you're reusing stuff a lot, then this should help massively in getting compute times down. Um, and also, if when you're testing it, you actually find that it seems to be caching things it shouldn't be caching or so, make sure to get me a test scene to check it out. Um, because I'm trying to make sure that it doesn't cache things it shouldn't cache. But yeah, you never know. And yeah, the values that it caches right now, let me just look. It caches colors, vectors, integer values, scalar values, a projection, as well as a matrix, which is super rare anyways. Um, there's a few other um, inputs, outputs that nodes provide, depending on the context, like the material, for example. But for many of them, they're either extremely hard to cache or it wouldn't really make sense in the way that Lightwave operates. So yeah, um, yeah, I'm afraid that's pretty much everything that I can show you today. There isn't much more. Yeah, it should work within NodeMeister. Yeah, absolutely. It should also work perfectly within other nodal contexts like deformations or things like that. Um, it should yeah it shouldn't be a problem at all. The biggest thing is that within shading it also has to take care of recursion, but that seems to work also at the moment. That's why I also had the reflecting floor here, because that means that it's going to be computed here on the floor as well, which is a different recursion level than the height of the cow itself, and just to make sure that at least it doesn't crash. The inputs, outputs are the same as those of, they depend on the data type. So in this case, projection is white. That's native Lightwave. But you can see once I add like an integer, like the item ID, that's that color. Ray position, which I think is a vector, so it's three doubles, that's blue. Weight, I think is a single scalar, which is red. So yeah, as you can see, they adapt the color of the data type, just like everything else. And I think that in Lightwave, oh, I see, I think that should be yeah, that's a matrix. Um, and I think in Lightwave, most of them, except for more complex ones like projection or so, have their own color. But that's done automatically because I say this input has the type matrix and then it gets that color. You actually can't change the color from the SDK. Would be nice, but you can't. And again, if you made a mess like I just did, you can go to the node menu and just say flush unused connections. Click on the node editor again because it needs to refresh the drawing of the node, and everything, all the trash is gone. Um, yeah, I think that's it for now. So yeah, as I said, if you have any nice use cases, any surfaces, anything um, where you would like to, where you think this would be useful, feel free to send me some sample scenes, sample surfaces. Um, if we can actually make them available for other patrons, that would be even better. Maybe I can think of one that makes some more sense than this one as well, and actually shows the render time difference a bit more, because obviously the projection node doesn't take that long to calculate. And the big stopper, just because some of you might be asking of why we didn't do this one earlier, because it existed before, is that the 2018 renderer actually removed um, one point of information that the cache node used, and that was the number of the current bounce when you're talking about rays. And the current bounce number is used to differentiate different levels of the cache. Um, because you might have a case where, let's say, the cache node on the first thread is computing, um, let's say, something, a surface that's here on the reflection of the cow, and then that again bounces into the cow itself, and on the second bounce, it would compute the same node graph again, but it would need to cache a different value. So I need to differentiate between the different evaluations of the node graph on different threads as well as on different recursion bounces just to keep them separated. And that means I need to know which bounce I'm on. And that information was actually removed from the SDK, even though oddly enough it's actually exposed here in the node editor. But I did find a way to kind of compute that myself. Takes a little bit longer, which means that the cache node isn't quite as effective as it could be, but it should still be okay. So yeah, other than that, I did rewrite some of the code, and I used the way the elbow node treats the inputs and the outputs to make it more flexible. Because I think to have the cache node adapt to whatever you want to cache is nicer than to have a fixed one with like a fixed set of inputs and outputs. And then if you want to cache two vector values, you need a second cache node because, yeah, that's how the old one worked. So this one is a lot nicer when it comes to caching different values. But yeah, um, I'm afraid that's all we have for you today. Thanks for joining us. Feel free to ask any more questions on our Discord, Patreon, whatever. And yeah, remember that we will be pausing our Patreon again in an hour or two. So if you want to join, now is a good time. We did also make the plugin, the tools available as like a one-time payment on a shop on Patreon for $10, which is an option in case we're pausing for people that just want to join in and get the current set of plugins. But yeah, so thanks for joining us, and yeah, have a nice weekend, and we'll see you guys around. Bye bye.